Located in South Wales, Aberthaw is a 1,550 megawatt pulverised coal-fired power station comprising of 3 units. The station was commissioned in the early 1970s and typically consumes some 5,000 to 6,000 tonnes per day of low-volatile semi-anthracitic coal, primarily sourced from local mines. This translates to around 250,000 to 400,000 tonnes per year of fly ash. Historically, most of the ash was landfilled due to the fact that the high carbon and ammonia levels of the ash rendered it unsuitable for use in cementitious markets. This created a number of issues for RWE Empower. Apart from the cost of landfill and the maintenance of the landfill site, there were increasing concerns being raised by local stakeholders over the ever-increasing size of the ash deposits. In 2004, Lafarge Cement UK opened up discussions with RWE Empower with the view of establishing a fly ash processing plant, CelticAsh, to supply its cement operation, conveniently located on a site adjacent to the power station. CelticAsh offered many potential benefits for both companies, these being: increasing the use of fly ash in cementitious products would make a significant contribution to reducing Lafarge's environmental impact, both in terms of a reduction in CO2 emissions and reduction in the need for quarrying of limestone and shale. The use of fly ash will enhance the properties of concrete and mortars. The avoidance of landfill would offer significant cost savings and environmental benefits for RWE Empower. The return of high carbon ash to the coal belts from the power station would offer significant fuel savings.
In 2006, and after a period of lengthy negotiations, Lafarge Cement UK and RWE Empower arrived at an agreement to jointly fund the investment and operation of an ash processing plant at Aberthaw Power Station in South Wales. The actual share of the funding was based on an open book analysis of the relative financial benefits accruing to both parties. The £8.9 million project comprised of some 10,000 tonnes of ash storage facilities, truck outloading and weigh bridges, ST equipment and technology carbon separation, high carbon return to the power station coal belts, ammonia removal from the ash together with an ammonia scrubber. The ammoniated ash was a result of ammonia injection to improve the performance of the electrostatic precipitators rather than NOx reduction, the usual cause of ammoniated ash. At the time, there was only one other plant in the world designed to separate ammonia from the ash, and this was based on STET's patented technology first used in Jacksonville in the United States.
The power station generates fly ash, which is transported to 3 silos. We tend to take from the middle silo and we use blow pots to blow it across into a 15-ton silo in our factory. We use a rotary valve to control the flow into the STI machine, where we separate the high carbon from the low carbon. The high carbon is then sent via a blow pot into a high carbon store which we've got in our plant. From this store we screw feed the high carbon up into a weigh hopper so we know exactly how much we transport back to the power station, and we then use a blow pot to transfer the material down into a 150-ton silo on the stock ground. From this silo we use a rotary valve again and drop it into a weigh screw, where we then add 20% moisture to make a condition that's transportable. We then use chain conveyors to send it up and drop the material onto the belt only when they're coaling for the power station. The low carbon, one of the characteristics here is that the low carbon is high in ammonia. So when we take the low carbon from the separator, we then transfer it into a silo, 60-ton silo. Again, using a rotary valve, we control the flow into a weigh screw where we add 0.6% lime. This is then sent into a pin mixer where we add 1% clean water. There's a very quick mix happens here where we then drop it into a pug mill. The pug mill is where the reaction takes place, and basically what happens is the lime and water drive off the ammonia from the ash particles. We then drop it into a mixer feeder and we screw feed it into a dryer. The dryer dries off the moisture and leaves a clean ash particle and ammoniated gas. The clean ash particle gets stuck on the outside of dust bags, drops down into a blow pot, and the blow pot then transfers it back into our stores, ready for dispatch. The ammoniated gases pass out into an ammonia scrubber, where the ammonia is taken out of the gas, and we end up exhausting clean air and send the ammoniated water back to the power station for their water treatment plant.
So this is where we take the feed sample, the ash feed sample from. This is where we take the low carbon ash sample from. And this is where we take the high carbon ash sample from. We test the low carbon ash every half hour in the furnace. We record the results on the spreadsheet with the feeds and the carbon, and this gives us the average yield for the hour.
Okay, this is the start of the ammonia removal process. The ash goes into this silo here, it drops down into a weigh screw, and then this is the lime silo here. It gets put into a feed screw, and it goes into a weigh hopper, and then that joins the same feed screw then, and it goes down into a pin mixer. Okay, the blend of ash and lime then drops into this pin mixer, where water gets added to it, and it creates a real intimate mix. The mixture of ash, lime and water then end up in the pug mill blender here. It's a slower blending process. The ammoniated gases then get vented off into the filter system. The mixture of ash, water and lime then drop down then into the feed screw. Okay, then the output from the pug mill blender then drops into this feed screw, which then feeds the ash into the dryer system. This now is the dryer system. When the ash gets heated up, it goes up there into the final product filter, which then drops into a flow pot, and then we can choose which store that we put our ammonia-free ash into. Okay, here we have the ammonia scrubber. So the ammonia gases come through the system, get scrubbed with water, and then we send ammonia-free gas then to the atmosphere.
The typical LOI of the incoming ash is between 12 and 22%. Typically we see 16% as average. The LOI of the low carbon ash is below 4.5, which is the standard that we work to. Generally 4%. The LOI of the high carbon ash is generally around the 45% LOI, but it has been known to be as high as 55% LOI. The typical yield is about 75%. We do get to 80, but we do get as low as about 65. Again, it all depends on the incoming feed LOI. It generally takes us about 5 minutes to start at the separator and about 10 minutes to shut the whole system down. The CelticAsh operators are often aware of issues with the power station before the power station even know. Sometimes when we see the relative humidity go up, that indicates a tube leak. Often we see the ammonia levels go up, we'll indicate to the power station the ammonia is high, and they'll find that they've got a leaking tap on the ammonia system. Typically the ammonia incoming feed is about 200 parts per million. When it gets to 300 parts per million, we'll inform the power station to say that it's high. After 10 years operation, the STI separator has proved to be quite a reliable piece of kit. The only thing we tend to change are the belts, some rollers and some bearings, but all of which are pretty easy to maintain. Belt life here at CelticAsh is now very good after we reverse the polarity. Typically we see 1,000 hours. We tend to change at 1,000 hours, but I have had one belt last 1,500 hours.